there's something wrong.
You simply have to open.
Yeah. This
yeah.
is.
Okay. Click. Yes, very good.
Yeah.
So maybe, Gerhard, you would like to say something about the 27th of May?
Yes, yes. The next Monday is a legal holiday. And so, well, as law-abiding citizens, we shouldn't do mathematics on Monday after the next Sunday. It's Pentecost. We will have a meeting at an unusual time on Thursday, 27th. At the same time, Dr. Gerhard Wind will talk on his recent research on primitive near-rings, prime ideals, and so on. And so and then the next will be the 7th of June. So the next meetings will be on 27th of May, Thursday, and then Monday, the 7th of June.
What time? The same as usual?
Same time.
Okay.
Time, yeah. We have participants from various countries with a different local time. And so we have to find, well, some decent medium time. And it turned out that Central European time, 13:45 will be good. All right. Yeah, should we start? What do you think? Yeah. This will be on 2 primitive near-rings with DCC with descending chain condition on right ideals, minimal condition on right ideals. I begin with repeating the notation, the definitions, the concepts, and I'll give a summary of number 6.8. Gamma, as always, will be a group, not necessarily commutative, not equals not 0. G, a fixed point free group of automorphisms of gamma. M, the nearing of all, as we called it, G transformations of gamma. And since gamma is not equal to 0, and we have the other conditions, we have gamma M is equal to gamma for all gamma in gamma star, that's gamma minus 0. Let Bi be the family of all orbits of G on gamma. That can be infinitely many, of course. Since we assume that gamma is not 0, this family is not 0. So that's a kind of a picture. We have in gamma the 0, that's an orbit for itself, and then orbits Bi, call it Bi, B2, and name it as you like. And since G is fixed point free, all the orbits have the same cardinality, the same length. G is fixed point free. Consequently, the Bi have equal length. G and this length is equal to the cardinality of G. Well, and then we introduce an element of M, the nearing of all G transformations. EJ is the identity map on BJ and 0 otherwise. And then we have these formulas. Gamma EJ is delta IJ gamma for gamma in one orbit EI or 0. And if I multiply this with M, then we get delta IJ gamma equals gamma for gamma in BJ and 0 otherwise. We have a mapping of EJM into gamma, which maps EJ small m onto gamma EJ small m. And this turns out to be an N isomorphism. Well, I should say an M isomorphism, yeah. For all J in I, EJM is N isomorphic to gamma and is a faithful M module of type 2. Yeah, this is I corrected it, but not in the copies which I sent. So we have that for all J in I, EJM is a minimal right ideal of M. Now let EJM sub plus be the additive group of this M group. We form the direct sum. For former times I called this distributive sum because it's a sum of M submodules, and then you this is stable under right multiplication. So from the definition of EJ, we infer that S must be a subsum of M plus, subset of M. And by some results from the paper, on some structure theorems for 2 primitive nearings, we get the following proposition. S is not 0, S is a right ideal. M equals S if and only if G has finitely many orbits. This condition is abbreviated by FO normally in the literature. And any two-sided invariant subnearing U of not equal to 0 of M contains S. 1 and 2 are very easy. We prove 3. First, EJM intersection with U is either 0 or EJM. If this intersection is 0, we have EJM times U is EJM contained in EJM intersection U, and we are in the case that this is 0. So U is contained in the annihilator of A EJM, and this is 0 since EJM is M isomorphic to gamma, and this is a faithful M module, so we have U is 0, or this is a contradiction to our assumption that we are in this. Yeah, that U is not zero. Hence, Jm is contained in U for all I, and S must be in U. Now we keep this notation and these assumptions and assume, in addition, FO, G has finitely many orbits. The situation is this: we studied nearing modules of type 2. And the main theorem on these structures was the density theorem, and we have certain consequences. If we want further information, for instance, on two primitive ideals or two primitive nearings and so on, we have to assume additional conditions. Let's try first FO. G has finitely many orbits on gamma. Then, that's relatively easy. Then M plus is the direct sum of finitely many minimal right ideals. Each one is M isomorphic to gamma. Hence, M plus has a composition series, being the direct sum of finitely many minimal right ideals. It has a composition series. And by the Jordan-Hölder theorem for operator groups, M must satisfy the DCC, the descending chain condition, and the ACC, the ascending chain condition on right ideals. And any dense subnearing N of M must be equal to M. This is, more or less a topological argument, which is quite nice even in the algebraic context. To make this topological argument clear, we insert, so to say, a footnote on the finite topology. We have the same notation for gamma and M in M. We define S gamma M to be the set of all mappings from M, all G transformations from M, which have the same effect on gamma like M. S gamma M is the set of all F, such that gamma M is gamma F. Now we form the set. Well, that's a special type of set S. We form the set of all those S gamma M for all gamma and all M, and define this as, or choose this as a subbasis for what we call the finite topology on M. This topology is here denoted by a special F. The set of points is M, and the set of open sets is called by O. This is the set of arbitrary unions of finite intersections of sets in S. We form all possible finite sets of finitely many sets in this special S, and form all possible arbitrary unions. And this defines the topology called the finite topology. The nearing N, nearing N is dense in M in the sense of F. That means for M in M and any finite subset, gamma 1, up to gamma s of gamma, there exists an n in M, such that GIM is GIN for I equals 1 up to S. So we are dealing with this finite subset. And this is more or less the statement of the density theorem. In the density theorem, we have the pre-images in different orbits, but an element of the G transformations, an element M from M respects the orbits. If, let me say, the G1 and gamma 1 and gamma 2 are in the same orbit, then gamma 1 M and gamma 2 N are appropriately defined. So that's fine. That's exactly what the modular slight change of notation. It's exactly what the density theorem says. Now assume FO, G has only finitely many orbits on gamma. 0, which must be fixed, and then B1 up to Bs. Say, then an element M of the nearing of all G transformations on gamma is uniquely determined by by gamma 1M up to gamma Sm, where gamma I is in Bi. The gamma 1 up to gamma S are orbit representatives. Hence, N in N is dense in mg gamma if gamma M equals gamma IM equals gamma IN for I up to 1 to S. That means if if N is dense and capital N is dense in mg gamma and small n is an element of N, then then if gamma IM and gamma IN are equal, then this leads to N equals M. And this means an element in a neighborhood of M must be equal to M the 1 point elements are neighborhoods. So N must be N mg gamma, and F is discrete. This is the end of this footnote. I like this topological argument. It's very I find this impressive. Now, again, we assume N is a nearing with identity to primitive on gamma. G is the group of N automorphisms, and we know G is on, it's too primitive. We know G is fixed point 3. N is dense in mg gamma. And we have now the following proposition, that N satisfy the DCC for right ideals. Then we have FO. G has only finitely many orbits on gamma, and consequently N is equal to mg gamma. Well, let us put that was proved in our last session. We put the results of this section together in the following theorem. Let N be a nearing with identity to primitive on gamma. Let G be SS orbits and so on. The whole liturgy. Then the following statements are equivalent. First, N satisfies the DCC for right ideals. N satisfies the DCC and the ACC for right ideals. So the DCC for right ideals implies DCC plus ACC. And we have, if FO, G has finitely many orbits in gamma, N must be equal to mg gamma, and N has only the trivial two-sided invariant sub-near-rings. That's a consequence of what we know on this S. And fourth, the finite topology F is discrete. Now, it's funny, we can say that the statement 4 may be considerably improved. We can show, same notation, FO is equivalent to F discrete. Proof in this direction follows from the theorem, and this theorem is just a conclusion of a summary of what we did mainly in the last section. So this follows from the theorem. The converse may be proved by, well, that's maybe it's a Tübingen specialty contraposition. We show non-FO implies non-discrete. So assume that's logically equivalent, as you certainly know. So let G have infinitely many orbits on gamma, and let N in mg gamma be in ng gamma, and U a neighborhood of U. We have to show that this neighborhood cannot be a one-point neighborhood. There exists a finite subset gamma 1 up to gamma s greater or equal to 1 of gamma such that U contains the intersection of these sets S gamma I, N, where S gamma I n is defined as above. That follows simply from the property of this decorative S, or the set of all those S being a subbasis. And yeah, I just repeat the definition of S gamma I n. Without loss of generality, we may assume that gamma 1 up to gamma s are non-zero and belong to pairwise, that are non-zero, yes, and belong to pairwise different orbits of gamma. They are orbit representatives. Now we choose, and we can do that since this any finite set of orbits doesn't exhaust gamma. We can choose a gamma s plus 1 in the complement of the union of those orbits gamma g gamma 1 up to g gamma s together with 0. Gamma s plus 1 is hence not 0. And then we have for I equals 1 up to s plus 1, we have gamma I e j equals delta ij gamma I. And now we define two elements, M1 being E1 plus and so forth plus and so on plus ES times N. If you apply this to a gamma, you can change to gamma E1 plus gamma E and so on, gamma E1 plus and so on plus gamma ES times N, and M2 being the same plus ES plus 1. And the E's have a clear definition. Es plus 1 is the identity map on the orbit number s plus 1 and 0 otherwise. Well, if we define in this way, then M1 and M2 are contained in this intersection I from 1 to S comma In. And now we have to distinguish two cases. If gamma S plus 1 N is not equal to 0, we have gamma S plus 1 M1 equals 0. Which is not equal to gamma S plus 1 N. Hence, M1 must be not equal to N. If gamma S plus 1 N is equals 0, no? Then we have gamma S plus 1 N2 is gamma S plus 1, and that's not 0. So again, we have M2 is not equal to N. So U contains at least one element distinct from N. And that means F cannot be discrete. This is maybe that's a bit arrogant to give you an exercise. It's don't take it too seriously. Let M be a non-ring with identity. U may be 2 primitive on gamma, and G the automorphism group, the group of n-automorphisms on gamma, and then we U let be a 2 invariant subnearing not equal to 0 of N. This U may be proper. This must be M again. I'm sorry. That's the force of doing all this all the time the same, writing in all this the time. It must be M. Roof U extends in M. Hence, it is too primitive on gamma. That this is an easy and obvious converse of the density theorem. So this concludes what we discussed and studied in 6.8. I decided that this subdivision of these numbers might not be useful, and so I changed my methods a bit. So we now 6.9, let N be a non-ring with identity 2 primitive of gamma, G as always. And yeah, I said at the beginning, if we have if you have a dense subnearing of this M, we must know some more if it's dense, and if we have some type of finiteness condition, it's equal to M. If we want substantial results, we need weaker assumptions. Now, let N be an N, and gamma N minus 0 are disjoint unions of G orbits, may be restricted to gamma N. We repeat this tilde gamma tilde delta is G gamma equals G delta. And now we define a rank. That's a formula, and it's a bit unhappy. I mean, rank N is the cardinality of the set of G orbits on gamma n distinct from 0. It's clear that rank n is greater or equal to 0 for all n, and rank n is equal to 0 if n is 0. And FO means G has finitely many orbits on gamma. That means the rank of one of one m is finite if rank 1 or n 1n is finite. If rank n is set S, then G has S plus 1 orbits on gamma. S plus 1, not S, because 0 forms an orbit. Now assume n contains a minimal right ideal K. That's the additional assumption on our primitive Near-ring. Then gamma is n equal to K, n isomorphic to K. Hence K is an n subgroup of n of type 2. These types go over by n isomorphisms. Second, there exists an idempotent E such that K is En and Ek, and it's a centralizer. C, semigroup of endomorphisms, of n endomorphisms of gamma, and En are isomorphic semigroups. That means this I means we have we'll see that's n isomorphic to gamma. We have gamma on which n is of type 2 primitive inside n, and we have the centralizer inside n in the form of the semigroup ENE. The semigroup of endomorphisms of a group of an n group is a semigroup. It's a monoid because it contains the identity, and it's a semigroup with 0 because it contains the 0 endomorphism. And any element K has rank K, in particular this E. Well, first, since gamma K must be not equal to 0, there exists an element gamma such that gamma K is not equal to 0. But gamma K is an n subgroup of gamma, and we have type 2, so gamma K is gamma. And tau, K to gamma K goes to gamma K, is an n epimorphism. We want to show that this is an isomorphism. First, the kernel is K intersection with the annihilator of a gamma. And since gamma K is not 0, we had this before, we have the kernel cannot be K. But the kernel is K intersection A gamma. And this is the right ideal of n contained in the minimal right ideal K. Hence, we have kernel tau is K intersection with R gamma, which is 0, must be 0. Hence, tau is an n isomorphism. 2 has 3 subdivisions. We start with 1. There exists an element in K not equal to 0 such that gamma E is gamma, hence gamma E square is gamma E is gamma. Hence gamma times E square minus E is 0, E square minus E is in K intersection A gamma equals 0, hence we have E is an idempotent. since E is not 0, in EK we have EK is not 0. Now mu, yeah, mu is a mapping from K to EK. K mapped to EK is an N isomorphism. We have that already. Hence, EK is an N subgroup of K of type 2. So we have K is EK equals EN. And now this strange semigroup isomorphism. Let C be the centralizer endomorphism, N endomorphisms of EN. We show that C is isomorphic to ENE, this an isomorphism of semigroups. Since gamma is N isomorphic to K equals EN, we have this N endomorphism of gamma is semigroup isomorphic to the N endomorphism of EN. And this is N endomorphism, this is an semigroup isomorphism to ENE. For for all N, we form the N endomorphism Tn. This is clear, and this is to be proved. It's a bit disturbing. For all N, we form the N endomorphism Tn, which goes to EX to ENX. ENE is EX, that's ENEX. Hence, EN, that's if ENE is EME, we have Tn equals to Tm. Now we define sigma from ENE to C in this way. Obviously, sigma is a semigroup homomorphism. This is clear from what we already have. If Tn is Tm, we have ENX must be EMX. Oh, we have Tn equals Tm. ENEX is TNEX. Is TMEX is EMEX for all x, particularly for x equals E. So ENE is EME, and sigma must be injective. You see, we work on the mapping from ENE to C. It's injective. Finally, let C be an element of capitals of this, an element of the endomorphism semigroup. There exists a P in N such that ZE, that's the mapping of E under this endomorphism Z. This, there exists a P such that E is EP, because this remains in EK. Hence, EPE is, we just insert EP is at EX, and that's an endomorphism. So we have ZE square, that's ZE, and we have ZEX is ZEX is EPEX equals TPE. So for all x, hence this Z, that which we have chosen is equal to P, T sub P, and S is surjective. We have already have that sigma. Well, it's injective, and we have its surjective and injective. And surjective means sigma is the isomorphism we were looking for. Now that 0 equals k be an element of capital K, we have rank k greater than 0. Assume rank k is greater or equal than 2. That means k goes over more than one orbit. Then there exists gamma 1, gamma 2 in capital gamma minus O, such that under k, gamma 1k and gamma 2k are not 0 and are in different orbits of G. The density theorem implies there exists an X in N such that gamma 1k goes to an element non-zero and gamma 2k goes to 0. They are in different orbits. That's possible. Hence, we have that kx, which is non-zero, is in k intersection a gamma 2. K is a minimal right ideal. So k must be contained in a gamma 2. So gamma 2k must be 0, which is a contradiction. And we are done. We wanted to show that a neighborhood of an element contains at least 2 elements. Well, is that, let me see. Right. Now, let me give a preview what we will do next. In 1967, I was in Leeds and worked with Hulkamp, and Hulkamp was preparing his thesis, and he could profit from what I knew on 2 primitive 0, 2, and 1 and 2 primitive near-rings, and he in his thesis he investigated 0 primitive near-rings on a gamma with certain conditions. He assumes that the set of non-generators of gamma is an N group of type 0, which must have generators, but also non-generators. Not all the non-zero elements are generators. He assumed that these are unions of N subgroups, and I shall give a sketch the results of Hulkamp in his thesis. And then there is another point. These near-rings of mg gamma, these near-rings of G transformations have been investigated to a considerable extent, and they were called centralizer near-rings. I think it's not good. They should have been called bicentralizer near-rings, because one forms the centralizer of a centralizer. And I'll give an overview with as little technical details as possible what is now the state of the affair on these centralizer or bicentralizer near-rings. Yeah, and this then we will conclude our study of the primitive near-rings and turn to near-rings which have several primitive ideals, maybe infinitely many, maybe finitely many, primitive ideals of different types. And it's it turned out that it is very helpful to study the intersection of all the primitive ideals and the factor near-rings, called them semi-simple. We saw that the factor near-ring modulo two primitive ideal is finite in the sense that it doesn't have any ideal, but that's a very special situation. We are looking for the situation where we might have a family of different primitive ideals, and this will be, yeah, the next point will come, and then we turn to what I will call Jacobson radicals. And the third point which I would like to discuss we might look for near-rings generated by the endomorphisms of a group. They are what is called distributively generated, and there's a considerable field of research on distributively generated near-rings. They have very close connections with groups, very close links, one should prefer to say. And this, I hope that this will be, yeah, I expect this will be finished at the end of June. Let me repeat, we will have the next session on the Thursday, the 27th at 13:45 time of Linz or time of Tübingen, and after that, after the 27th of May, we will have our next session in June on the 7th of June. All right, that's for today. Are there questions or? Could I now cancel the picture? Maybe, yes.
Okay, now we're here. Gerhard Wendt will continue on the 27th of May with just these things, primitive near-rings, primitive ideals, connections to prime ideals, because a lot of new insight has been gained in the case of zero primitive near-rings, and so we'll have information on that on Thursday in 1 week.
You mean as sort of summary?
Yes.
at the beginning of our session on the 27th. Yeah.
Yeah.
Well, I could have prepared this today, but this wouldn't help. This I think we should be able to recall what we did. I know there is a lot of technicalities, but I found, maybe I was wrong, I found at least a considerable part of the lecture should be down to earth, with hard work, doing all the proofs and not just giving results. But I think that Dr. Wendt will more give results, and maybe it should be repeated. I should repeat a few things. Yes, definitely, no problem.
I mean, you don't have to do anything. Gerhard Wendt will do this, and he will present new results as well concerning 0, 1, and 2 primitive near-rings.
Well, if he will do that to the extent as he needs it, fine. Yeah.
Okay.
Okay.
Well, then, thank you very much. See you again.
See you on the 27th.
1.5 weeks. Yeah.
Yeah.
Goodbye.
Bye bye.